Okay, subduction, geodynamics, and again, some incentive to interrupt me, especially if just ask any question if I begin to just get into a monotonic drone, whatever, ask any random question to help us out. And so this is a talk. There's this old fairy tale about subduction zone curvature being related to a ping pong ball. And I think it's a good starting point because some people have seen this and it's even in textbooks. So I want to convince you at the end of this talk, Earth's not a ping pong ball. I've done that, then I'm successful. And I want to impress upon you that 3 dimensions is really profoundly influences things. And I think you saw a little bit of that from the Andes talk where we took a very simple model, but because we think that tectonic setting is inherently 3-dimensional, then we start to see some things that we start to explore new areas, and so we think that problem for sure is inherently a 3-dimensional problem, and probably a lot of the subduction zones are as well. So we'll give a little background, static forces, and then we'll kind of do a little survey of the planet and get a perspective on the diversity of subduction zones that exist. And this is full of stuff that probably you should see at some point in your career if you're thinking about subduction zones, just random compilation. And then I'm going to focus on what we've been doing for a good 5-6 years. And it's fairly mature now, and we can make predictions and use these very simple models to learn something about plate motions. And I'm grateful to Tobias setting the stage perfectly for me to continue where he left off. And it's very exciting new stuff about how plates that aren't attached to subducting slabs are moving. And this is going to be the other side of the coin. I'm going to focus completely on the slabs that are driving plates. Okay, and I'm going to try to explain or convince you that it's really just to strengthen the weight. These 2 factors are controlling subduction on Earth, and then I'll give a survey of how we apply this to the Earth. Arc curvature, slab morphology, and the partitioning of plate motions, and you'll see what I mean. So we covered this. The reason I brought it up before is because there's no giant mountain range here. This is a typical subduction zone. The Andes are very atypical because there's a huge mountain range. Okay, that's missing from here. And again, I think it's public domain. So this nice radius of curvature here that you see, this is how we like to think about subduction. And a tangent to that would be the slab dip. That's what seismologists would see. And certainly there's a slab dip in the shallow area here. It's exactly linear. So these things, if you download the talk, are things you can stare at. Oh, sorry.
Sorry, in that diagram, you're saying that the typical subduction zone has the back-arc extension?
No. This is kind of everything that could happen in a subduction environment. So it's, but they all do have an arc, and they do have a forearc and a back arc. And sometimes there's extension in that back arc, and you'll have a basin, and sometimes the extension will be big enough to actually generate a back arc spreading center. So those are less common. And sometimes there's an accretionary prism, sometimes there isn't. We'll see that. So in the early days, there was this classification of a Chilean type, the shallow, this Pampean slab that people are mentioning, where it's shallow or flat lying. And it has different stress environments. It has this shallow prism. And then there was this Mariana type where it was a steep dip. And there was some tension here, and there was very little, there's more of a rollback component. Okay, and then we heard about this erosive aspect to the margin, and that's called an erosional type. So here we got a Central America, and you see a nice deep trench there. There's the reason you see that is because it's not covered in sediments. right? Over here, you don't see it. This is Pacific North America, Pacific Northwest. Where's the trench? It's covered in sediments. It's a big prism here, okay? And this margin here has been measured to have some erosive aspect. So this, you can go around the planet measuring where there's, which ones are erosive, which ones are accretionary, and maybe which ones are more Chilean or Mariana type. And so this is another attempt. There's always, every couple of years, a new attempt to classify subduction zones. And what the correlation is here, well, when you get this big accretionary type, and it's also a Chilean type, then you can get, these are the ones that make huge earthquakes. So those are more interesting. We should think about, why there's magnitude 9s in here. There is some correlation, but I don't think it's exclusive. But that's one motivating factor. What causes great earthquakes? So that's
where are the ones in the very bottom of your table?
Sorry, yeah. These ones here, Peru, Japan, Kurile.
Where are they?
Hmm?
Are they randomly dispersed? Looks like they're all over the upper left-hand side.
Yeah. Yeah, these are by classification and not listed in order of magnitude.
Yeah.
Right. So they're kind of grouped.
And it's the Tohoku earthquake which is violating this rate of relationship.
It's what? Tohoku? I expect it to be violated many times, actually. I think it's far too simplistic. Huh?
Which paper is that?
They're talking about, which paper? Oh, gosh, I left it off. Yeah, that's a big no-no. Let me, they started it, and this is an updated version of that, and so I'm just blanking on the name. I'll add that to the one I upload. Okay. Do you know? Okay. So a ping pong ball. If you dent a ping pong ball, there's this curvature. So is that why the Earth has curved subduction zones? And it's a nice little fairy story that you can tell people. And luckily, there's people that don't believe in fairies or Easter bunnies or even maybe Santa Claus. And so, yeah, we've developed an actual, there are dynamical theories that can explain this curvature, and this would be the overriding plate in this region here. So that's a motivating question. Why are the subduction zones curved?
So compelled to take the other side with the occasion right.
So here's some things that the ping pong ball would predict. Okay, there's this dent that we're looking at. So this is the curvature that would be predicted for a sphere. It would intersect this, and it would be its shape. It would predict a particular shape, which would be a small circle. We look around the planet where it's hard to even find one that's a small circle. And the next thing would be a relationship between curvature and dip age. Okay, so this means that the arcs that are curved more should have steeper dip. And that's not true either. There's many exceptions to that. Also, the highly curved arc, there are highly curved arcs. They tend to show the exact opposite. So places like Scotia, the Hellenic, the Mariana, where there's nice, sharp curvature, they are less steeply dipping. And they would also predict no lateral variation, that the dip is constant, the curvature is constant. I have trouble finding one that's like that anywhere on the planet.
The Caribbean
Is steep. But that's not, the Caribbean is actually about 1,900 kilometers, so it's, where Scotia is 600, so the curvature of that arc is more broad, but you can try to say it explains one and then calibrate your model to that one and then find that it doesn't explain any of the others. So, but the main thing is that this is a static view, that and these things we know from paleo reconstructions, the arc curvature is changing over time. And so this just can't be the case, that the things are static. And
So let me say a word in defense.
no, I'm not going to let you.
I've never known you to be less speechless.
I think there are many processes acting in a subduction zone. And so I wouldn't expect one process to totally dominate how it looks. But I imagine as a plate before it goes in is acting very plate-like. That is, it's inextensible, take a piece of cellophane. Once it subducts, if it's a ping pong ball or a piece of cellophane, it's inextensible. That would sort of tend to make a ping pong ball-like subduction zone. Now, as it subducts, it warms up and it's going to lose, especially its plastic strength, the yield strength of some sort. And then it's going to behave more viscously. So I think when people like Ken Krager look at the seismicity in slabs going down, they see not just down dip stress, but where the arc is different than you'd predict for a ping pong ball model. They see the slab being driven in horizontal extension or compression. And so I expect there are forces in the upper, say, 100 or so kilometers or 150 that are trying to make it ping pong ball-like. And they can be overwhelmed, but they are contributing some to the shape of the slab.
Okay, so deep inside every slab's and plate's heart, it wants to be behaving like a ping pong ball, but it's not allowed to because there's other physics that are swamping it out.
So I agree. So the question is, how important are the ping pong ball stresses compared to the others, especially as a function of depth or whatever?
I'm not going to talk about initiation of subduction zones, but I would just there's work, the Caltech group has done a lot of work in that area, and a lot of these environments where they're initiating subduction, there's a forced convergence, and that the plate needs to be forced down into the mantle quite some depth before it starts to become self-sustaining. And the types of plate boundary geometries that occur when there's a forced convergence, or I don't think this model would. Yeah. Okay. Well, I'm going to cover a lot of other things that will have some of these that describe some of these forces. So these are some of the places that we're talking about. There's the Aleutians, the Caribbean. That one looks like a nice curvature there. This one here, Scotia, is quite small, and there's Marianas. So, but if you start to look in detail, it's not just a nice single curvature that you see. It varies quite a bit. And here's two examples. This one here obviously flies in the face of the ping pong ball because it's the opposite direction. Okay, and this is another good example where Tonga Kermadec here is pretty straight, and then it starts to get highly curved right at the end. So those are things that just don't look anything like a nice, smooth, constant curvature. As far as variations in dip, I want to impress upon you that this varies dramatically globally. This is color-coded across every little transect. They've measured these little earthquakes and tried to estimate what the radius of curvature would be for that. And actually, Bruce Buffett had a paper just come out recently that he redid this, and they have a better constraint on this now. But in this, we just look at this histogram here, and it sort of peaks around 340 kilometers for the radius curvature. But there's a huge tail, okay, going up to very, very long, large radius curvatures. And and then we see that it's really hard to do this just based on dip angle. These two things are very different because it completely depends on where you measure this dip angle at, what tangent line you take from this radius curvature to call a dip angle. So that's why we like to think more in terms of the radius of curvature.
What happens if you just start from the arc, the volcanic arc down? Because at least in the
that's a very small portion of the entire slab.
Yeah,
So let's look at.
If you look at the forearc, the slab doesn't know if it's going to be flat or steep until you get down to about 80 or 90 kilometers. So if you're looking at the difference in slab dip along the
Okay, so then draw your tangent line somewhere below that, and it's still going to have a lot of variation, and there's a lot of variation globally. That's just, yeah, you're exactly right. Even on a small scale, there's large variations that you cannot say this particular slab has this dip angle or this radius of curvature. There's lateral variations over small distances. And then if we look at depth, there's not a continuous radius of curvature for all depth. Look at some of these wild, here's the Banda Arc, Indonesia, sorry, there's Banda, and just the whole Indonesian, Java, Sumatra complex, and several cross sections here along this trench. We've got use this here is 660 kilometers, kind of defining slab morphology in the upper mantle, and it's varying. It's pretty straight there, but there's a little opposite kind of curvature there, and then over here we've got like almost a rollover kind of situation. These ones here are from this Neotethys slab being subducted, or Indian plate being subducted. And then across these two subduction zones, these look fairly kind of straight shots in. And these are strange. So, because they don't have a curvature. They just look like they've been injected.
One of the things that's interesting about all the tomography images is that you don't actually see continuous plates very often.
That's exactly right. I've got a slide for that. So the issue is that this is looking from such a large scale, from so far back, that we don't really see. We know this is a subduction zone, right? But where does it connect? We've lost the connection. Where's the slab? We know this must be slab, but where's the connection? And is it 100 kilometers thick? You know, what's the thickness of this? It's actually bigger than 100 kilometers. So it's not a plate. It's not a single.
The resolution of those depths turns into something like 1,000 kilometers or something, just roughly. Where it's getting fat.
Yeah, there's a lot of thickening. I mean, it is a single subducted slab, but it's not a linear sheet. You know, it can't be because it's far too thick.
The resolution of the tomography, and I don't know the answer.
How much of the smearing?
So because the resolution is so, is in the range of 1,000 kilometers or something?
I think they see it a little better than that. You're outnumbered here.
What is the resolution in 1,000 kilometers depth, roughly?
The resolution, global images, the resolution in the upper mantle is by 4.
Is what?
In the upper mantle.
4 in the upper mantle in global models. If you have a local array, then you change that.
Yeah, so.
Does that mean that if you don't see it here in the tomography, it might still be there?
Yes, it could still be there. But there's also regional tomography models
So
that.
you can't take any conclusions from not seeing something.
You know, the more regional ones, there aren't a lot of really continuous slabs even in regional models. I mean, they show a lot of variation in thickness and they show a lot of segmentation. If you look at the Mediterranean images, you actually see things people interpret as pairs all over the place. And Steve Graham, who is one of the first tomographers to identify slabs in the mantle, said if they were 100 kilometers thick, he would never see them in the mid-mantle. So there's something else going on.
So they're piling up there, and that's why you see them.
They're doing something.
Well, in many models, they slow down and fasten up as they enter the lower mantle.
400 kilometers.
Yeah, right, the global size model.
So at 1,000, the mid-mantle depths is it? What is the resolution?
About the global tomograph, like a 2 degrees, so I thought this that doing the greater size.
2 degrees is
200, well, I think that's maybe.
Better than 1,000.
better than 1,000.
Satisfied. Okay. I'll use regional tomography models next time I show that slide. Okay, so here's some reasons why, and this is our map of subduction zones I'll explain these colors in a second. But yeah, these things all vary, and a ping pong ball type thing would predict no variations in trench curvature, dip along the trench, dip increasing with depth, and that they would not evolve with time.
Well, before you leave that, now, it's what King Craig calls a benching problem. If you have a subduction zone and the curvature is wrong and the slab goes in, you have too much slab length and it has to fold up. And one way of doing that is kind of turning into lasagna. And so if you look at the places where slab curvature is not right, you would predict slab to sort of shallow, for instance. Now look at...
but that's in a perfectly static model where everything's taking a path that...
Well,
and then there's sort of a conservation of volume issue. I get that you're losing volume as you go deeper.
It's inextensible. There's stresses trying to keep it in that shape. Okay, so what you have to do if the slab is going to dip steeply, where the arc is backwards, is you're going to take the slab as it subducts and shorten it horizontally as it goes down. And if it resists that, then that resistance will tend to buckle the slab. I'm not saying it's going to dominate, but it'll have that effect. But then I look at Altiplano area where the slab seems to be shallower, it's right where it's backwards. Under the Olympics in Cascadia, it's shallower. I look at Japan where it bends backwards and it's shallower. It looks like there's a tendency to hold slabs up where the arc is backwards.
Yeah, actually, that's what Brian Isaac's 1988
Exactly.
paper said in terms of the orocline and the shallowing, that it was reversed, that the slab was initially shallow in the center and has since steepened and shallowed on the sides.
The ripples have moved out.
Yeah, the ripples moved out.
I agree. Okay, I agree. The slab, there are more things than going on than that. But yes, buckling is important. Absolutely. A slab that's sort of a sheet that's being shoved into the mantle, it could buckle for a number of reasons. You know, one could be geometrical, one could be flow coming around the edges and pushing those edges to create a buckle.
Right.
But yeah, but all of this hinges on the fact that the slab in the mantle is already weak enough to buckle. And if it was a strong, coherent sheet, then it would be like a canoe paddle. Okay, it would just travel straight down. And
if it were totally inextensible piece of cellophane, then it would have real problems.
yeah.
So I'm just arguing that I think those stresses contribute to the geometry. And I don't know how important they are, but I hate to just leave them off the table because it alone doesn't explain the geometry.
Okay. Well, yeah, and I have work right now with my postdoc where that's exactly the phenomena that we're investigating in terms of the history of the Farallon slab. In very detailed reconstruction, we can see that there's a buckling, but we think that buckling is driven by mantle flow, and not so much driven. Is it driven by the mantle buckling the slab, or is it the slab just buckling if it was being pushed into a space that was too small? Okay. So go back to Tobias showed these forces here, and this is the Forsyth Ueda, the bottom-up perspective, I'd call it. We have all these different plate driving forces that he's introduced, and the drag force. Okay, and in the original conception, this drag force is dragging the plate forward. See the arrow of the drag force, and it's dragging the plate. And I think that, and he certainly had good evidence for this being important on plates that they're not attached to subducting slabs. So I think that, this kind of invokes a active upper mantle to drive the plates. And I think that's okay. But it's this slab pull. So this would be sort of the mantle dragging the plate above it and moving it. And okay, he's already shown that. And in this is an updated version here where the drag force is the opposite way, and it's actually a resisting force, not a driving force. And we can argue about this, and it's very maybe location dependent. So in this case, the drag force is acting opposite to the plate motion, resisting it, and the plate is being dragged over this more passive passive upper mantle as it's being pulled by a slab pull. And these are two conceptual end members, and we're going to just adopt the slab pull driven conceptual end member and move forward with that, knowing that we're just doing that for pedagogical reasons, not that it's a religion. All right. So forces that drive plates, again, I had this in my talk. It's already been introduced, and this is that slab suction mechanism where there's a sinking slab. It's creating that low pressure and that suction by inducing this larger scale flow, and that will drive these two plates towards that convergence. So it's a self-sustaining activity. Once you have something sinking, you're pulling more stuff towards that convergence zone. So in essence, that's a convergence. These are these observed plate velocities, and the key thing here is that the subducting plates, on average, are moving about 4 times faster than the non-subducting plates. So there's an inherent asymmetry that this plate here should be moving towards this downwelling 4 times faster, on average, than what that plate is. Okay, but this is actually symmetric, and if you only include the slab suction, you get a ratio of about 1.6. So it's off by quite a bit. So this is one of those driving forces that's shown up more recently. Now what the little detail that got left out is that they actually go in and put along all the subducting margins in an ad hoc way. They just pull it. They just add an extra force that's called the slab pull force, and it's meant to represent a stress guide from that sinking slab that's preferentially pulling the subducting plate. Okay, and that's why they get a much better, ostensibly better agreement between their model and the observed. But on this large global view, there are important differences in the flow here. For example, you could just pick. And this plate here seems to be wanting to go. Antarctica has a very different pattern of motion. So, there's differences. I think this is showing a different motion altogether for the Pacific plate than what is observed. So that's our motivation for just considering, this slab pull. Go, Melanie.
I forgot how the slab suction force is parameterized. So I guess it's a visual fraction or something that's being modeled?
Their model, so they iteratively find a slab pull at each little segment of subducting trench area that helps resolve a minimized torque in a way that will help the plate find better agreement with the observation. And so there's a variable slab pull being added as a line force.
And the subduction force, how does it work? Like, is it viscosity?
Yeah, it's just from a density-driven flow.
So it gives back a visual traction, and then that which you use in the model?
They're using that sort of the HC code, for this. It's Hager-O'Connell density-driven flow that generates flow, and then those pressure gradients will, induce the plates to move towards the downwellings.
Isn't there an observation
They go back.
that the velocity of the plate doesn't depend on the size of the plate? So that the slab...
There is an observation.
Maybe it's not an observation. It was an observation, and it's been modeled that slab pull is the force, but the resistance isn't related to the size of the plate, but it's related to the thickness of the plate, or the bending of the plate.
Yeah, that was previously reported, but it doesn't actually explain the plate motions when you look in detail. And in the paper that I'll present later on in the talk, this is one of the long-standing things that people have discussed. It goes back to the Forsyth-Ueda paper. That's where it was originally posited that this area of the plate has something to do with it. Yeah, but we went and looked at this again. It doesn't really stand up to a scrutiny. So
that's what I was just looking at this figure from Clint's paper with Brad Hager, where they argue that it's the lithosphere rheology that actually is limiting the
yeah. But that's not internally consistent. The bending that they have is not internally consistent with the radius of curvature that they have. So they're prescribing we'll talk more about this later. They prescribe a radius of curvature and also a velocity and also a strength in the lithosphere. So those things are not internally consistent. There's no actual slab that could have all those things at the same time. So that's why they get large bending dissipations.
But nonetheless, I mean, they've made reasonable estimates and calculated how much work is involved in digging these slabs. So, yeah.
These things are also dependent on these assumptions and some of, if you force two things to go together at a certain rate, and you force it along a certain path, okay, then you estimate how much energy there was. Then you've just described that system, but the plate will decide how fast it wants to go, and the plate will decide what its radius of curvature needs to be. And that, you let the plates decide that and then measure the dissipation, then you get a different answer. So that's why we tend to favor models that don't prescribe all of these things.
Well, I guess if I agree with that, nonetheless, there is work being done to bend a slab, and it
There is.
fairly significant.
Yes, but it's...
But it should be in a self-consistent model.
Yes, and I'm saying that the models that are less self-consistent amplify the amount of dissipation that's going on. It is significant, but it's not as much as what people had previously thought. I apologize for the little tiny letters, but I put this in for the students to look over in their free time. We get into some semantics very quickly, and so it's good to have some reference frames and parameters described in terms of kinematics. So what am I talking about? When I'm talking about the plate motion, I'm talking about the subducting plate velocity. Okay, this would be if we have, say, an overriding plate that's not moving and a subducting plate that's moving slowly. We can have some extension. If the plate's moving very quickly, we can get shortening, and that goes back to the convergence velocity, which is the rate at which material is being consumed from the surface and entering the interior. And it's important to realize that the convergence velocity, the speed at which material is leaving the surface, is not necessarily just the plate velocity. The plate velocity is just one part of that, because you also have to take into account whether there's extension or shortening or compression, because if a plate is extending or shortening, then that's actually being subtracted or added to the total convergence. And so the convergence velocity is measured at the surface. The subduction velocity is what we would actually characterize the amount of material going in the Earth. Okay, so the difference between convergence velocity and subduction velocity is that this is the rate materials entering the Earth. This is the rate that the two plates are moving together, and those two things may not be the same. Similarly, the trench can move, and so we call this trench migration or trench retreat. But the trench doesn't always necessarily retreat. It could also advance. So if you had two plates in an advancing trench, for whatever reason, you would also maybe see shortening. Okay, some of these things are reference frame dependent, and then we need to also account for any accretion or erosion. But this is down at the, these are maybe second order. And then if there's overriding plate velocity, okay, then So we want to mostly focus on the subducting plate velocity. That's what we just saw with global plate motions. Those are the plate motion is a subducting plate typically. The trench velocity, this can accommodate subduction. For example, slab rollback that's pictured here. Okay, this plate is fixed and not moving. The slab is sinking, and the trench is rolling back. But we are subducting material. We've subducted from there to there. We've subducted that much material. So you can have subduction without plate motion, forward plate motion, without a forward plate velocity. And all subduction has to happen either through this forward plate motion or trench retreat that's accommodating slab rollback. Okay. Why do some plates... What we want to do now is measure how much of this is happening at each plate and along how much does it vary along the strike of the different plates, or can we average and get some sort of average sense of how much each plate is, how much of the subduction velocity is partitioned between forward plate motion and trench retreat. Okay, so there's two ways a plate can subduct. That's critical to this.
So what's the reference frame?
So we're adopting kind of a Mantle reference frame, and that makes it tricky when you compare with observations because we don't really have a Mantle reference frame in the Earth. We have to guess what the best Mantle reference frame is, and then we assume that it turns out the Indo-Atlantic hotspot reference frame appears to be, sort of an Africa-fixed reference frame. Might be closest to a fixed mantle or a mantle reference, absolute mantle reference frame. Yeah, did you have? Okay. All right. So in the ideal slab-driven model, you can have this. So this is the slab pull. And the slab pull, it's pulling the plate. So we have some motion here. Okay, there's our fixed Mantle reference frame defined by a completely stable plume conduit, which doesn't exist. They all move a little bit. And so there's some plate motion. There's also some trench retreat. So the subduction is accommodated by both things. And that's a normal situation to have for most plates. This is possible, but it's certainly less common, where you have a slab kind of rolling forward because of this would be trench advance. If this plate really didn't want to move, and this plate didn't want to bend, then it would just get pushed forward.
Why do we see more slab rolling back? If slab pull dominates, I guess you would see the opposite, right?
We're going to explain exactly. We're going to look at how much of each this happens globally and why why the partitioning favors trench retreat. Yeah.
Wouldn't it be more reasonable to define trench retreat or rollback relative to upper mantle than lower mantle?
Well,
We don't have a reference frame.
yeah, I guess that.
But why do you pick a lower mantle reference frame?
Well, yeah, I mean, I guess we're assuming an absolute Mantle reference frame is like an artifice to begin with, that we can try to estimate various ways, but yeah, we have this. It's more of a concept to have a. But in the model that I'm going to show, I do have a reference frame. It's fixed by the geometry of the model, and the mantle's not moving in my model. It's completely fixed, and the plates are moving relative to it. So in the models I show, it's an absolute Mantle reference frame. So if the subducting plates weren't driving things, but the overriding plates were, for example, this might make more sense here. If this plate was moving very slowly and the overriding plate was pushing into it, okay, it would be driving subduction and causing some slab rollback. And so this is what people have sort of mentioned about South America, maybe. Okay, it's one place you could apply that. And then in this case, there's a static trench. So let's imagine that the trench motion doesn't move, okay, and the overriding plate can move away from the trench exactly the same speed that the subducting plate moves, and then we won't have any relative trench motion, but we'll still have subduction. It's just that it is moving exactly along the same path, and so it's kind of anchored in a sense. Conversely, we can have this. It'll be accompanied by some shortening if the overriding plate is moving this, opposite to the subducting plate. Okay, so you need to have some background in kinematics so we can look at the Earth and try to interpret what the plate motions are. And this is reference frame dependent. And we've looked at many different reference frames that exist. They're all summarized here. We actually look at 8 different reference frames. And what we find is that there is a pattern. Most reference frames, the Indo-Atlantic's probably the best, a hotspot reference frame based on Indo-Atlantic hotspots. And one that's the worst is one based on the Pacific hotspot group, and a particular version of the Pacific hotspot reference frame, HS3. So that would skew all the plate motions. And that actually turns out that the HS3 plate reference frame is one of the most widely adopted. Okay, and so a lot of the people have in mind what the plate motions are based on that reference frame. It's been a very popular one. Other reference frames would have different ideas, and in particular South America. Okay, South America is moving about 2 centimeters a year towards the west in this reference frame, and in the HS3 it's moving about 5. So this is really important. What you think, how fast South America is moving, completely depends on your reference frame.
Dave, you said some were good and some were bad.
Well, some were evil, and some fight for the,
What was the criterion of goodness based on?
Okay, it's subjective. One nice thing. Okay, that's a good point. I said that 7 of these agree almost very well. Very good agreement. Not much difference. And then there's this one outlier that happens to be one of the most widely used reference frames. And here's a few things.
I don't have any advice about this, by the way.
Okay, here's a few things. It could be South America that. So here's one key thing. Pacific plate. It's 8.2, 7.6, 8. It's going about 8 centimeters a year in this reference frame. In the other one, it's moving 10 and 11. Okay, so we would have to reconcile or explain faster Pacific plate motion in one reference frame or the other. Okay, I basically look at all of these and add about 2 or 3 centimeters towards the west to get a difference between the two for the other. I'm not going to show all of these, but let's look at the retreating ones are in blue. The ones that are roughly stationary, just moving 1 or 2 centimeters a year either way, are quasi-stationary. The other ones are advancing. Okay, and so those ones are in red. Advancing trenches are very few in this reference frame. South America, over here in Japan, and this one, the Macran. Okay. In the other reference frame, it's about 50% of the planet is advancing trenches. And now we could go look, well, where are all the mountains? All right? If all these trenches are advancing into their places, where are the mountains? Well, I know there's mountains there, and this is where this reference frame tends to predict the largest advance. Okay, we could also look at, well, which places are retreating, all right? Here, there's this little South Sandwich Trench, which is retreating and rolling back. And in the other reference frame, it's advancing. But we know from, there's geological evidence for some extension in that area. And also there's some extension here. Okay, there's a slight amount of rollback. And if you just start to look at this map and think about the geology, what's going on, what's the tectonic or stress regime in the back arc, okay? In some of these you'll find that these retreating ones have extension in the back arc, and that's what you see geologically. In the other reference frame, they would say they're stationary and the other plate's moving away. So we would say, we think it's the trench moving away causing the extension. They would say, no, trench is stationary and the other plate is moving away. But that's kind of a problem if the other plate is Eurasia. What's making Eurasia move? I don't know. What's making the trench move? That I can explain. Oh, yeah.
Do we really need to consider the absolute velocity with respect to the mantle to consider whether it's extensional or contractional? Isn't it the differential velocity between the trench rolling back and the other plate that is instrumental, irrespective of what the reference, the motion with respect to the reference frame is?
The convergence velocity is independent of reference frame.
No, the convergence, the differential velocity between trench rollback and upper plate velocity. That's the key point which will define whether you're in a contractional or in an extension.
That's also independent of reference frame.
Yeah.
And what I'm saying is that, but you still have extension at the end of the day. And you have to explain, is it the overriding plate moving that way with the trench fixed that's causing the extension? Or is the overriding plate fixed and the trench is moving away to cause the extension? Right? Like there still has to be an extension.
I mean, the difference is in different reference frames, you add a velocity to all the plates in a different reference frame compared to the interior. So you can imagine adding this kind of motion and say, what is the overall flow field associated with this? Add that to your model, and that's what I think Dave's objecting to. If you put this kind of shear on it, how do you roll back or advance to coincide with the overall shear that you've applied across the upper mantle?
Okay, so
One reference frame compared to another.
So just to really be clear here, this is the good model. What's this model called?
This would be Indo-Atlantic reference frame model.
So IAR1.
Yeah.
Okay, and then the one that we're supposed to not pay attention to is HS2.
3.
3, excuse me. And HS3, the big difference is Africa's fixed.
Yeah.
So you basically take the Africa motion, you have to add it to everything else.
Africa is actually moving this way. Here's another thing that's nice about this reference frame. Okay. We start to look at spreading centers, all right? What would be nice is if both plates are moving opposite directions, okay? Now the relative, the spreading rate is a spreading rate, and the plates are moving. But in the other reference frame, you have, for example, the Mid-Atlantic, okay? We have Africa moving away, South America moving away, and these plates are moving different directions from the ridge. In the HS3 reference frame, okay, these are both moving this way. There's a relative difference between the two plates that would cause that same spreading rate. But both of them are actually moving that way. So that's another built-in bias of mine that I prefer my plates moving in opposite directions of the spreading center.
But isn't the argument, if I remember correctly, that the hotspots in the Atlantic Ocean are not centered on the spreading axis, so there's a motion between the Atlantic spreading ridge and the hotspot position?
Yeah, that's why it's not perfect. The hotspots are moving, the groups of hotspots are moving, everything is moving. We think the Indo-Atlantic ones are moving slightly less, and the plume conduits coming off of them are not moving as incoherently as the groups, individual separation of plumes from you could also just argue whether there's plumes or not. So this could go all day. Right? I just want to make one point. Oh, go ahead.
I just wondered about timescales. Is the timescale of the trench rollback and advance the same timescales as that used to define these models?
A lot of these are sort of GPS derived in the and the plate motions are sort of averaged over longer times. But I guess, are you asking what's the source of describing these motions?
Is it an appropriate comparison to talk about whether the trench rollback or advance supports the model? Are they defined using, or do these models represent a longer time scale of plate motions or a shorter time scale?
Well, we only have a snapshot, for plate motions based on GPS. We have plate reconstructions, so we can look at reconstructions and see this if the pattern looks like it makes sense with the geological things. But at the end of the day, you can't say definitively. So.
For example, if you take HS3 and you get the trench out of the Marianas, for example, it's been advancing very recently. Right? So if you take HS3, for example, but you have a switch, so it retreats until, I don't know, 10 million years ago, and then it advances since 5 million years ago. So that's not, so I mean, that would tend to say that you're right, it's shorter time scale, much shorter trench functions, right? That's what's used for these models. Because these are all based, no matter what absolute reference frame you take, they're all the same plate motion, right? It's all number 1A. That's where we magnetic anomaly anyway.
This is a snapshot. My point is that, two, but I'll also, yours first. All of these subduction zone boundaries are dynamic features that are moving over time. And we're characterizing them here. We've added little arrows to what their motion is today. But this changes over time. So this is just a snapshot of a dynamic system where everything's moving, including all of the trench boundaries, okay, or subduction zones. And that the pattern is we have a lot of retreating trenches, about 50%, and then the next largest amount of trenches are basically quasi-stationary, and then very few advancing. And if we look in a different reference frame, we get a different sort of distribution of which are retreating, which are advancing. So those are the two key things. And that we have about what we're calling about 24 distinct subduction zones where there's like a coherent plate that's subducting under, we can call that one system. So we have to have a finite number, and that this finite number of subduction zones, they have a different lateral extent. And this is why the study of these subduction zones is inherently three-dimensional, because this has a different lateral extent than this. And so they should behave differently. Okay. And there's an order of magnitude variation. The smallest one here, the Betic Rift in south of Spain, is 200 kilometers, and then probably the longest would be like this system and this system. It's both around 6,000 kilometers. Okay, factor of 30. Okay, so these are points that we could say are open research questions. Why do plates subduct the way they do? What controls their stability? How do they evolve over time? How do they interact with the overriding plate? Especially, this is crucial for trying to understand flat subduction, okay? Because the overriding plate is playing a huge role in that. What controls this variation in dip angle? That one is just not answered. So, I keep getting questioned about it, but I don't have the answer. It's an open question. So, at a certain point, have plates always subducted the same way that they are in modern plate tectonics? We only have records that go back so far. We see that there were convergent zones in the past, but did they look the same as how they have been since the Cambrian, if you want to say that's when modern plate tectonics started? And then, it's always fun to think about other places. Is a subduction, could it occur anywhere else? Venus, Mars, super Earths? So, okay. You've all had a primer in mantle convection, and that was a really good overview. And now we're going to just focus on, we're going to abstract mantle convection to in a very simplistic way. We're going to abstract that thermal boundary layer, where the plate is cooling, into a viscous sheet of uniform thickness and strength and density. Why can I do that? Why I can't really, but why? What would motivate me? What madness would cause that? Let's imagine that we have the Pacific, and at one end of the Pacific, it is subducting, and it's 120 million years old plate, and then it's got a few thousand kilometers. Okay, so maybe a few thousand kilometers is kind of the initial size or length of the plate in my model, and at the tail end here, it would be about 70 million years old. Okay, well, that's like 50 million years, but what's the thickness variation? We're assuming that the plate starts this, whatever reason, small scale convection or various other things, that the lithospheric thickness thins after a certain age. There's a flattening of the heat flow, would suggest. And so we're just looking at mature, what we'd call mature oceanic lithosphere. Okay, so this entire plate would be mature oceanic lithosphere. It's all older than 70 million years. Okay, and we just say if it has the same thickness and it has roughly the same negative buoyancy. Okay, it can move. It has a free end, so it can move through forward plate motion. It has a free trench. We're not telling the trench where to be or what geometry it needs to be. And so the trench can also move forward or backwards. And so this is not being forced to move or be told where it needs to be. Okay, so it's kind of free in that sense. It's driven only by that density difference, and that density difference is an estimate of how, if you have some thick oceanic lithosphere, how dense it would be relative to the underlying mantle. And our asthenosphere here goes down about this far, and it's not nearly as exciting as Tobias's asthenosphere. So we've simplified all of those details into just a Newtonian single viscosity. And so this would be the subduction velocity. Let's add those two together. And there's an interesting thing. We've left this little bit of room here between this side of the plate and the wall, and that's so that this flow can move around the edge. And so that's why we say each slab has a finite width, and around that edge, mantle can flow around. And this is observed several places where there's seismic anisotropy showing flow around slab edges. And so that's important, that this boundary is far enough away to not influence the system. Okay, so it's got a little room there, not corrupt the results. We call that flow a toroidal flow. It's so you can decompose a velocity field into a toroidal component and a poloidal component. That poloidal component is that thing that's familiar to you, that corner flow, that circulation that goes. It's always sort of up and down, whereas this is more of a lateral flow.
So how long does the plate have to be before you get away from the effects of toroidal flow?
So good. That's excellent. If you were a student, you would be going home with this right here. Sorry, I disqualified you. Okay, this flow here has a length scale. Okay, and this plate here, it has a length scale. And the critical thing that Alan's hit upon is that if this length scale is bigger than the plate, then the plate is entirely engulfed in this toroidal flow. Okay, and so how big is that flow? That's one of the things that we kind of just look at the, we try to vary the width of the plate and assume that this toroidal flow is always about the same length, and it depends on the assumptions that we make for the mantle viscosity. But then we look at systematically. Okay, let's imagine this toroidal flow is about the same size as the plate, and then let's make them about equal. Or sorry, that this toroidal flow is much larger than the size of the plate. And then if they're about equal, and then if the plate's really, really long, then this, and is pictured here, this toroidal flow will only be acting at the edge. And so we're going to systematically look at those. That is the essence of what's controlling plate motions in terms of understanding their width. And then really quickly, I want to talk about how we simplify the lithosphere, which is unfair to everybody who's been modeling very temperature dependent and stress dependent and all the kind of difficult things that go on in here. We've simplified it like like a Zen monk that would just kind of meditate on this and say, what's the essence of the problem here? There's a brittle crust that has a finite strength, so it can break. Okay, that's sort of a necessary requirement. There's a strong core inside the plate, and we need that because we know that there's this stress guide. There has to be a way for the falling slab, the sinking slab, to pull the trailing plate. And for that, we need this strong core. And then underneath, it starts to warm up a little bit, and there's some creeping. And so we basically have a little sandwich here. It's strong, but it can break and become weak. It's always strong, and it's not that strong, but it's stronger than the surrounding mantle. Okay, and so that's our simplified lithosphere structure. And then and so these are the equations that we solve. This is the density, the driving density difference here. Okay, and gravity. So as Tobias explained, this is things that are more dense are sinking, and so that would be our sinking plate. And we have conservation of mass, and that's it. So I've ignored an important thing, which is the advection of temperature. Okay, and sorry, this is actually the viscosity that gets stuck in there if you're in this zone here, but otherwise it's the viscosity that we've prescribed. Yeah, Max.
Is your momentum equation really correct in that data appears outside of elsewhere?
You can write it. That's a simplified. I mean, you can write the full vector description of. You can write the stress tensor. So I could make this, grad dot sigma if you want, but that's just a.
But you have non-homogeneous viscosity.
Yes, you're technically correct. Yeah. So the equation needs this eta inside here, which is if we had a completely uniform viscosity everywhere, then this would be correct. Okay. But it's not. But don't worry, we do solve the correct equation in the code. Okay, so I've neglected temperature or advection of energy. And the reason for that is that there's diffusion, but diffusion takes a long time. This boundary layer, we already said it's mature. It's already thickened as much as it will be, and it's not going to thicken anymore, right? And so that's why we can sort of ignore this getting any thicker over time, because it's sort of reached its maximum thickness. Okay, and so that's one of the reasons we...
Does your slab get weaker as it subducts?
It does get... No, it does not. As this part sinks down, it doesn't heat up and lose any of its strength. It's already pretty weak to begin with, though. So, and then we only consider the top part of the lower mantle. So this whole box is 1,000 kilometers, and that's because this is more viscous than the upper mantle. And we find the slabs, they start to rest upon this viscosity increase. And on the time scale of the model, they don't really sink that far into the lower mantle. So we don't need the whole lower mantle for them to sink through. All right, so I've described this structure. And this is important. We have not prescribed anything other than the density of the plate, or the buoyancy, and the strength of the plate. And that's it. We haven't forced we have not prescribed any velocity or any location of the trench. So these things are going to be emergent quantities. I think that's what... we're also not prescribing a radius of curvature that other people would have. And so we just have a flat Earth. The mantle's a cube, and there's no thermodynamics. So everything okay with that? And we also have no other plates, I should mention. We're just looking at one plate, the sound of one plate subducting. we say. All right, this is more of this about this toroidal flow. This little pictorial diagram here. There's two toroidal flow on each side and a poloidal underneath, and this corner flow, that's the other poloidal flow. And in this case, you see this slab is so small, it's actually totally engulfed by this toroidal flow that gets induced around the slab edges. So this is what we would classify as kind of a narrow plate, because it's much smaller than the toroidal flow being induced. And it also happens that when flow starts coming from around the edge of the slab, it totally wipes out the corner flow that's in the middle. Okay, that corner flow in the wedge here kind of relies on a two-dimensional geometry, and this third dimension is allowing that toroidal flow and wiping out. Is allowing this return flow around the side and wiping out the corner flow to some extent, because that destroys the pressure gradients that are helping drive that corner flow. Okay. And then finally, as this system evolves, there's a trench curvature that starts to develop. So we always start with a linear trench, and then it evolves to some shape. Now, I didn't invent these models, and a lot of people have done similar models, and probably over the past 10 years, a lot of authors have made contributions with these types of models. So our design is actually based on trying to emulate some laboratory experiments so that we can kind of achieve an agreement, or that way we can maybe convince ourselves the numerical models are representing things that were observed in the laboratory, which is a nice place to start before you start making having the numerical models do things that the laboratory models can't. So we want to have that one milepost we both met up on. Okay, and so I'm summarizing here a couple different styles. All right, this one here is, notice it's got a straight trench and it's subducting, retreating backwards. Well, that's because it's so strong that it's not deforming, even though there is some flow coming around the edge. And this is a cartoon representation of all the different styles of subduction that have been observed in all of this work. Okay, everybody's run different setups, different materials, different viscosities, different densities, and for the most part, all of those experiments you can find they'll exist as one of these styles. And the challenge,
Two questions: the base of the model,
yeah,
or is the boundary between the upper mantle and the lower mantle?
For the most part, yeah. I mean, it's in this cartoon, yeah. This would be the 660 in most places, yeah. And this kind of folded pile here, this would slowly start to sink and deflect that 660.
And the second question is, so all this work ignores the youngest part of the plate, so you're always cutting it off at 50, 70 million years. So in the force balance, you don't have to drag the younger plates along, is that correct? Or will that change things?
We don't have like a plate going back. We kind of assume that there's this jump at the ridge. Yeah, that's just like instantly, 70 million years. So.
In the laboratory models, are the folds forming at the bottom of the tank?
Yes.
So it's
So that's the bottom of the fish tank right there in the lab models. And then in our virtual fish tank, some people have had it just be that depth, and then we have a viscosity increase, but they're broadly similar. Yeah, so we've got these 5 styles, and the one thing people have been describing the viscosity of the plates, but what does that mean in terms of strength? That's one thing that was lacking in terms of understanding what's the real strength of the lithosphere. And some people were actually running similar models and getting different styles, so that was worrying. Yeah.
I'm curious about, so you're drawing these narrow little strips of a plate, and obviously in the real world we've got actually a plate on either side. Mm-hmm. And so, do you have any insight into how that might affect things? I mean, are you basically assuming that you have an infinitely weak boundary?
Yeah, we are, because we're starting with one plate, and then when we understand how one plate subducts, we add the other plates and try to understand what the difference is, how they're influencing the system. So at this point, where I'm showing you, we're assuming no other surrounding plates, and we're just trying to understand how one plate subducts. This is where we're at in our understanding. Like, we can understand one plate and then start to add the other plates and build from there.
There's a paper on that, right? By Mantle?
Yeah, do you want to talk about that? Can we turn the recorder off? There's a model where they take this, but they surround it with other plates. The other plates are attached to the walls, and then they show a snapshot in time of the subducting plate. I've never seen a model evolution. I've just seen a single snapshot, and I don't think that their model is able to produce a reasonable evolution. So I'm not convinced that it's all having those other plates, that they even have a system that's subducting. Think about that paper. You have 4 Oakland Raiders linebackers, each holding a limb, and somebody comes up and asks you, "So how fast can you run right now at this moment?"
I'm not sure that one works. But it is true that all of
So this plate that I'm saying, in that model, the plate's not allowed to subduct because the surrounding plates are completely dominating it.
But I think pretty much all of these have been observed seismically, as well as in tank models. I mean, the multifold one, I'm not sure, but the overturn subduction zone and the flat one and the single fold and the very steep one.
Yeah. Yeah, I mean, these are, this could be sort of derivative of that. You know, the main difference here is, I'll show you in detail what the differences are between the different styles.
I think there's one place where it looks.
I've got images of folding. I don't know if they're regional or not. So this is the only thing we're prescribing is the strength and the weight, and so for now we need to understand bending. Okay, so imagine here's your plate subducting down. And there's your radius curvature, and this length of slab here is like a weight that is applying a bending moment at the what we call the subduction hinge. Okay, so the weight of the slab is applying this bending moment, and it's going to be proportional to the length of the slab and the thickness of the slab. That's the weight. The weight of the slab is sort of just its mass, and it's resisted by the strength of the plate here. This is the plate that's supporting that length of slab, and so that's what's going on in bending. It's a competition between how strong the plate is to support a length of slab and how heavy that length of slab is. Okay, and the nice thing is that these slabs are changing their length over time, and so you can have situations where if you have and also the strength here is probably changing with time as you subduct younger plate material. Okay, so that's too hard, and that makes my brain hurt. So we'll just assume the strength is constant and the weight is growing with time. So only one thing is changing.
How important or irrelevant is the weight of the continent by the moment?
Yeah, so our models don't have this continent here, and it's a good question, Gene. The circulation that happens here is this corner flow acts as this hydrodynamic suction. It's a lift. It's hydrodynamic lift when you have a fast circulation in here, and that lift will cancel out some of this weight. So it'll cancel out some of the bending moment, and therefore make this slab be apparently lighter. Okay, so then what we're actually looking at here is the effective bending moment, and there's a lot of other things that could modify that. But this is probably the largest amount. Alternatively, you could subduct something like a big oceanic plateau, and that big oceanic plateau gets sucked down here, and that's going to change the weight because that's compositionally buoyant. So that would also modify the bending moment. Okay? And so we're not considering those. We're just going to try to understand how it works first, and then hopefully future studies will build those in.
You don't have that low pressure due to the corner flow in the wedge?
We don't have an overriding plate, so it's not effectively, it's coupling to a free surface rather than a viscous plate on top. And so if we had a viscous plate there, it could couple, that would produce a little bit of lift, adjust the radius of curvature a little bit. Yeah.
Did you use an overriding plate to have a suction, to have a lift?
Well, to have a strong lift, yeah. Because we just have a free slip surface, so there's nothing.
I thought that was a circulation.
There is a circulation, but it's once you clamp. If you have a thick plate, you're decreasing the area of the wedge, and so you can increase the circulation, and that will help, increase that suction and the hydrodynamic lift. Okay, so how do we describe a bending moment? We call that M. It's a force times a distance, and we want to integrate that over the length of the slab. So that's L. Okay, and that force is just the buoyancy. It goes by the thickness of the plate, and so we have a little proportionality to this L squared. And now here's a critical assumption in this analysis is that when we have a radius of curvature that's not as nicely drawn in this cartoon, we want to say that the moment is saturated and that any length of slab larger than its radius of curvature is not actually contributing anymore. So it's kind of moment saturated. And so we're going to replace that L with an R squared. And then the plate is being resisted here. The strength of the plate it's a viscous sheet in these models. And so we have this parameter, which we call the flexural stiffness, and that's for kind of the analogy of a bending beam, and it has a rigidity. Okay, this is the viscous sheet equivalent of that, and this is the speed at which material would be going through, the strain rate going through this thickness. And so that we can relate to the subduction velocity and the radius of curvature squared. So that's this part. And then this is this flexural stiffness parameter, and it depends on the strength of the plate as described by the viscosity and the thickness of the plate cubed. So the thickness is extremely important in controlling. Okay, that's the big, you see power 3, that's massively important. So we want to relate the moment of these two moments. They're two moments that we can set equal, and say the strength of the weight, the moment it can support, the strength of the plate and the weight of the slab, and we can quickly derive this, where this is of Stokes buoyancy. If anybody, I like to plot things with BS on one axis. So. And the Stokes buoyancy is the density, sort of the Stokes density, just the buoyancy of the slab normalized by the upper mantle. And then finally, I want to non-dimensionalize this because that was a dimensional flexural stiffness. And in order to non-dimensionalize it, I can define a flexural stiffness that would represent the entire upper mantle. Okay, and so I divide the flexural stiffness of the plate by one that would be, the same expression for the upper mantle, and I can get a nice thing here. This is what people use in the lab, typically a gamma, a viscosity contrast between the plate and the upper mantle. So that's nice because there's lots of data that people have done their experiments with that. And then this is the thickness of the plate to the depth of the mantle. So similar is what, we want some kind of scaling, and that will go to the cube. Okay, now a little tour of some pictures here. We call this the viscous beam mode because it's got this straight trench. And these are really strong slabs. This plate is strong enough to support and you even see it kind of just looks like a beam that's getting bent. So very strong slab, very strong plate. The subduction velocities are fast, but it's mostly through retreat, and this plate doesn't move very far. Okay, so it's dominated by trench retreat, and it will have a slab lie down completely flat. And this is a huge radius of curvature right here. Okay, so much bigger than the depth of the upper mantle. And this is a little model here. I'm going to freeze it real quick and point out what we're looking at. This is the second invariant of the strain rate. The axes are covered. It's the log, so it's very sensitive to deformation. And things that are red are under high deformation, high strain rate. Things that are purple have low deformation, so they're basically moving. There's very little in deformation. And so I use a log scale to show that this is effectively not deforming. This viscous sheet is actually behaving very plate-like. And we see where there's a large gradient. That's our proxy for where the trench is. It's actually where the plate sinking into the mantle. There you can see the radius of curvature. This gray surface is the viscosity contrast. It's so 660. We've got some velocity arrows showing a cross-section of the horizontal flow, horizontal component velocity. And what else are we missing here? Yeah, and so we also look at the strain on the back walls. That tells us if those stay mostly purple, that means there's not much flow or deformation out there, and our walls are far enough away to not be influencing the system.
What depth? That's a shallow slab, but what depth would it be? Do you have any depth scale on that?
Yeah, this is 660 kilometers, this surface here. And we're also only simulating the left half, if you want, of the slab, because everything's symmetric. And so there's another mirror symmetry, a mirror domain here we're not simulating because we're exploiting that symmetry and throwing all our computational resources just in this half. That allows us to have this extra wide box and make sure this boundary here is not going to influence the flow that's going on over here. So this is the viscous beam. See a nice flow developing. Straight trench, not a lot of plate motion, and it's just a plate subducting through trench retreat and creating a very straight, canonical-looking subducting slab, if you want. You know, that's a cartoon textbook version. And then this regime here, the advanced fold retreat mode, where these are heavy and they're strong. Moderate subduction velocities. There's a little bit of curvature that you'll see develop here. And the neat thing here is the trench advance. We have plate advance transition into trench retreat. Should fix that typo. There's a single we call recumbent fold. Once this tip hits the bottom here, the slab transitions to retreat. And it's sort of got a medium radius of curvature. So here's this one. It's retreating. There's a little fold here, and that single fold that's what they do. And there's been several lab experiments that have seen that. There's a transition between that transition there is actually because the weight of the slab is increasing over time. So initially the slab's not very long, and even though it's heavy, the plate is strong enough to support it. Okay? But then as the slab gets longer, it's heavier, and the weight of the slab becomes dominant over the strength of the plate. And that's exactly why this little transition occurs in that model. Then we have strong slabs. In this case, no matter how much slab length is subducted, the plate is always strong enough to support it. And so it always keeps a constant radius of curvature, and it only wants to bend so much, which is there's a maximum bending moment. It's moment saturated for sure. So this entire length of slab, no matter how big it gets, can only apply a certain load, and that is insufficient to bend the plate much more than that. So we have also a medium radius curvature, and then once the slab tip hits the 660, there's this roll forward that's been seen. So you can see this one. We like to call this one the umbrella handle, or in some versions it has like a little more like an elephant trunk. So I like to give these names. Advancing mode is better if you're...
Why it's advancing?
Why is it advancing? Okay. It is advancing, so at this point, the plate's moving forward, and then at a certain point, the slab tip hits the bottom, and then both the plate is moving forward and the trench is advancing. And the reason is because it's this length of slab that's producing the weight that's bending the plate at the hinge, and once it's saturated, it wants to maintain this radius of curvature. And so you don't have anything to bend it further. And so in order to maintain that radius of curvature, the trench and the plate both advance together. Okay, finally, something that looks more Earth-like because it develops some curvature. And so this is the retreating mode. We get fast subduction velocities. Trenches are curved. It's dominated by trench retreat. And these create these flat-lying, backwards draping slabs. And so this would be kind of your basic small Mediterranean type slab. I should point out that all the models I'm showing you have the same width. So we're keeping width constant at this point. And you see this little flat-lying slab. There's lots of flat-lying slabs in the transition zone that people have observed. So but what's nice is that you have a flat-lying slab, but on the surface you've got some nice trench curvature developed. And then there's this folding mode. And so these are the weakest slabs. So they're completely, all the surface expression of the trench is being dominated by what little details are happening in the upper mantle. Very highly curved trenches. And these actually have a strong partitioning. This mode here, it depends strongly on the width of the plate. And if it's a narrow plate, it'll be more dominated by trench retreat, and if it's a wide plate, it'll be more dominated by plate advance. So these actually depend on the width quite strongly. And then there's this slab pile from this recumbent folding, and they have very tight or small radius of curvatures. So this is the folding mode. Oh boy, stomach's going to start grumbling. So here's a little survey. We've been able to reproduce all of these tank experiments in the lab. Now here's our folded material. This Neil Reeby put some markers on this. 400 kilometers. Okay, it says far bigger than 100 kilometers. But we see at least in this model by Zhao, there's about a feature that's 100 kilometers in thickness in the upper part of the mantle. But when it gets down here, it's thickening. Something's going on 3 to 5 times. So maybe this is the product of this folding at the transition zone, and then that instability is slowly sinking into the upper mantle. So in that view, the viscosity increase is acting like a low-pass filter. And if it's not going to fold, then the plate is just going to lie flat. But if it's a stationary trench and it can fold, it can make a bigger pile, and that pile can start to sink. Yeah.
Can you see some trench shadow?
We have not seen too much of that, but I think it probably exists in some of the models. Yeah. Okay. Here's our regime diagram. That's that flexural stiffness that I described. The weaker, stronger, lighter, heavier. All the regimes kind of plot nicely into these little areas. And so this is with just those 2 parameters, we can describe the entire spectrum of behavior for these subducting slabs. And so that works pretty well. We also measure the radius of curvature, and then we predict what the radius of curvature should be using those simple scaling relations that I showed you. And so I'll let you read these real quick. I think I kind of described this as the models were running, and you can look back at that if you want. But one thing I want to point out is that this line here is separating two-dimensional slabs from three-dimensional slabs. If you want significant curvature, then you have to have a sort of a three-dimensional situation. Okay, we've seen this, and I use bending moments. These are there's a trench, and these are the outer rise topography, and you can also measure the gravity and use that ratio to estimate what the bending moment is on slabs at Earth across a couple profiles. And then I've tried to translate that into what would be an equivalent flexural stiffness and Stokes buoyancy. But the thing I don't know is the viscosity of the upper mantle. So there's all these big ellipses here. And I've converted that into a shaded region, which I could plot on my regime diagram and say, oh, well, look at that. Yeah, exactly right, Alan. It's depending where you are on the Earth, you could get any one of these behaviors, okay? But, for the most part, we see a lot of things happening right at this boundary between the folding mode and the retreating mode. Okay, so put a big Earth. It's a huge.
So you're planning regime 1 for the sonic system?
Yeah, I am. I know. All right, chapter 5. How are we doing? Everybody's hungry. We got to get moving. Yeah. All right. 12:02. Should I just end it then? Or?
You have 50 results.
I do. Yeah. I'll just. Let's see. Okay, I can do this in 5 minutes. Okay. All right. Narrow plates. I think we've covered that they were good. Scotia, Mediterranean. There's Italy. And the Caribbean, we'd call those narrow. They're basically retreating trenches, and we've seen a similar version of that. The wider plates here, these kind of quasi-stationary, and they develop into piles. There's a pile by Vanderhilst and Sino, and some tomography by Brian Kennett. And I don't think you've seen the piles already. I'll put these movies on in the CIDER website. You can watch them, and then the very wide plates, the toroidal flow is only acting at the edges, so you get retreating edges, which is maybe what we see, Patagonia, and up here there's a little bit of extension, so maybe the edges of the South American plate are moving. And the key thing is that we think that this folding behavior is really telling us something. The slabs are weak. We see that Reby, sort of showed, there's these 400, 500 kilometer thick piles, and maybe they're the products of a folded slab. All right. Yeah.
Sorry, but you said you don't have temperature in there, so they could get weaker anyway, even if you had temperature.
Yeah. But another thing is that if you want to observe them in the lower mantle, a good way to preserve that signature is to double it a couple times, because then the diffusion, it's not going to diffuse away as it sinks through. So take a 100-kilometer slab, fold it a couple times, 300 kilometers, it'll last 1 billion years. You can see it in the lower mantle. All right, we've tried to summarize what the plate velocity is, and for all of these different subduction zones, and plotted them versus width. There is a little bit of a correlation, and this is backed up by a fluid dynamic theory, so that's 16 of them. And then we see that the ones that are smaller tend to favor more retreat. And if we look at that ratio of how much of the total subduction is done just by forward plate advance, then we actually see for all of these places where we've done that average, we get a fairly good description. And I'll just point you to our paper here that gives that full dynamical theory to explain why that happens fluid dynamically. These are our model results here. So that was nature. That's what's going on in the Earth. And these are for our models and using our fluid dynamic theory. So I think that this trend of partitioning narrow plates mostly retreating and wider plates mostly advancing is pretty neat. So I'm going to skip over this and just finish with the Laramide orogeny. And if we go back to 52 million years, the width of the Farallon plate was huge, and there was a lot of compression. Okay? And that's what we start with 50 million years ago. So here we are at the trench parallel slab width, and we're right here at this peak, and it's dominated by forward plate motion. Some crazy stuff happens. There's a big orogeny, there's a flat slab subduction, there's all kinds of things going on at this point, but what's also going on is that the Farallon is starting to break up and its width is decreasing, and then it finally starts to segment completely because of this triple junction, the birth of the San Andreas Fault. Then we have one large plate break into two smaller plates, which now don't want to be one large plate advancing. They want to be a couple of smaller plates retreating away. And this is the exact same time that you get a lot of extension in the overriding plate. And yeah, there's been a lot of stuff happen in the meantime. Flat slab subduction, everything getting welded under, Laramide orogeny. But we started with compression in a wide slab. We're ending with two narrow slabs and a lot of extension. And that's what we basically want to point out, is that here we are with it, and then based on that reference frame, it's a retreating trench, and there's still some further extension. So that's kind of our model for why we had this transition from a compressional overriding plate in North America to an extensional, and that it's driven by this shrinking width of the Farallon slab. Okay, good. Thanks for all your questions.